We will be discussing our paper on a non-parametric online changepoint detection algorithm. Changepoint detection using the cumulative sum algorithm, or CUSUM for short, is a well-studied problem, and some useful variations and enhancements to the basic CUSUM algorithm have been proposed. However, CUSUM algorithms require the user to specify one or more parameters specific to different signals. This paper presents a set of additions to the CUSUM algorithm that eliminates sensitivity parameters using several new automation techniques, allows easy extensibility to generic non-mean changepoint detection, and makes it more adaptive while maintaining causality at all times.
Changepoint detection is fairly well studied in literature. The basic CUSUM algorithm uses the generalized log likelihood ratio test with two user-defined parameters. Delta, which is the minimum change in mean that should be flagged as a change point, and H, which is the threshold that a cumulative sum Gx must exceed for the algorithm to flag a change point. Adaptive CUSUM, or ACUSUM, was developed to adaptively choose the threshold value H used in the CUSUM algorithm. This technique primarily focuses on using an ACUSUM chart. The ACUSUM charts are effective in accurately detecting shifts in the mean of the signal. However, in order to detect changes in generic features apart from the mean, one would have to rederive the code of the algorithm and use a completely new ACUSUM chart. Adams and McKay's Bayesian Online Changepoint algorithm is the best known online changepoint detection algorithm. By modeling the occurrence of a change point as a random process, BOCPD has proven to be an effective and robust approach. The algorithm only uses retrospective data to make predictions, so it is capable of being applied in an online setting. However, the performance of this algorithm decreases when detecting changes in a feature other than the mean of a signal.
In our work, we introduced a multi-domain, online, adaptive, non-parametric algorithm for changepoint detection, or MOANA for short. MOANA is an extension to basic CUSUM, summarized on the left. MOANA estimates delta and H autonomously. It is adaptive with live mean and standard deviation updates. It is easily extensible to detecting non-mean change points effectively, and it is causal, so it can be applied to stream data. Here's the overall pipeline for MOANA. The pipeline includes 3 stages: an offline training stage, an initialization stage, and a detection stage. We will now dive into the details of each of these stages.
Let's get started with the autonomous delta estimation using regression. We have developed a regression technique to estimate an appropriate value of delta, eliminating user-defined sensitivity parameters. A regression model will always have some error. In order to reduce the effect of this error, we propose using regression to predict the number of change points present and then find a delta using this, instead of directly predicting delta. The process to train a model is detailed in the figure on the slide. To train the regression model, we require signals and their corresponding number of change points, both shaded yellow in the figure. We then extract signal statistics X for each signal. The statistics used are dictated by the application. For example, for audio signals, zero crossing rate and signal length are effective features. Ultimately, we use X and the number of change points to train a regressor to predict the number of change points based on these signal statistics. Training is done offline before running MOANA. During inference, if more than 2 change points are predicted, we search for a delta that yields the predicted number of change points for the signal until that time. We insist on more than 2 to maximize the likelihood of having seen upward and downward changes before estimating delta. Until the delta is predicted, MOANA will not perform any detection. Finding training data for delta estimation is fairly trivial, given most tasks that require segmentation also requires classification. So that means labeled data would already exist. We use said labeled audio segments to create training data, which are signals with known number of change points, to perform regression. As such, no additional labeling is necessary.
Next, we will discuss the live mean and standard deviation updates. One of the reasons MOANA is adaptive is due to the live mean and standard deviation updates. We initialize the mean and the standard deviation using the first I samples of the signal. We found I equals 20 to be a reasonable balance between enough samples for accurate standard deviation updates and initiating detection as early as possible. However, this can be changed if desired. For each sample of I, MOANA updates the mean theta naught to be the average signal amplitude since the last change point. Activity before the last change point is irrelevant to the next change point. We cannot follow the same approach for standard deviation, sigma, as too few samples yield an inaccurate estimation. Thus, at each sample I, sigma is updated using an exponentially weighted moving average of the current sigma and the standard deviation of the last I samples. This method allows more recent samples of the signal to have a more significant impact on sigma, while never using too few samples. If changes occur in the first I samples, the initialization will be skewed, but Moana recovers due to its adaptivity.
Now we'll go into details about the dynamic estimation of the threshold value h. Moana dynamically estimates the threshold value h for the generalized likelihood ratio test. As mentioned earlier, the threshold value is the minimum value that the cumulative sum must exceed during the GLR test for the algorithm to flag a change point. Because we're detecting changes in both directions, we opted to use two distinct thresholds, h up and h down. These values are directly related to the average running length, or ARL, defined as the estimated number of samples before a change point is expected. These thresholds are determined by the algorithm based on the ARL. To calculate the ARL, we treat the signal as a simple Markov model with two states as shown in the diagram. State SI is the initial no change state, and state SF is the final change occurred state and is an absorbing state. In state SI, we assume the signal is constituted of samples that are being drawn from a Gaussian distribution with parameters theta naught and sigma, which are calculated using the live mean and standard deviation update approach. And in state SF, we assume the samples are being drawn from a Gaussian distribution with parameters theta naught plus minus delta, depending on the direction of the change, and sigma. The instantaneous state of a signal can be completely described by the probability of it being in state SI and the probability of it being in state SF. Based on this Markov model, we can create a transition matrices for each direction, up and down, as shown by TNE in this slide. Keeping the Gaussian assumption in mind, the probabilities in the matrix can easily be calculated using Bayes' rule. We can use this transition matrix to calculate the ARL using this equation. It is to be noted that SF is a sinc state. Thus, we can only solve this equation if we assume an empirical approximation for this state. Given an ARL, we simulate a signal Y with a change point that occurs at the ARL. The threshold is the cumulative sum of this synthetic signal and is calculated using this equation for H. What if a task solely requires segmentation and no label data exists? For this purpose, we provide a parametric variant of Moana using a newly introduced parameter, beta. We propose an option to indirectly hand-tune delta using a more intuitive domain-limited parameter, beta. Our approach is inspired by bit error calculations from communication theory. The algorithm assumes that the signal is derived from a normal distribution with mean theta naught before a change and theta 1 after. For simplicity, we assume the standard deviation for both distributions are identical and are equal to the standard deviation of the signal in question. The sensitivity to change points is related to the overlap of the two Gaussians, which can be used to calculate a bit error rate. Similar to the expected bit error rate calculations, we define a quantity called expected change point rate, or CR, which can be calculated by the equation shown on the slide, assuming equal probabilities of change in either direction. We can then re-express this equation as a function of a new variable called beta using the complementary error function as shown. Using this formulation, the higher the beta, the more resistant Moana is to detecting change points. As such, the user can choose Moana sensitivity based on the application. Beta is a domain-limited parameter and can take on values between 0 to 10, as it is directly dependent on the length of the signal, which is highly unlikely to exceed 10 to the power 10 samples.
Several change point detection methods perform poorly when applied to features of a signal other than its mean. For example, many methods make an explicit or implicit assumption that they are tracking the mean of a random signal with a specific distribution and degrade significantly when that assumption is not met. At its core, Moana performs mean change point detection with a Gaussian assumption. However, due to its data adaptive nature, it can accommodate different actual distributions. Thus, applying Moana to detection using features other than the mean by transforming the signal into the feature space still tends to yield robust performance. We've also conducted experiments to empirically demonstrate Moana's robustness to different distributions. We present our results to this paper in three parts. First, we will segment voice therapy exercise samples into regions of importance and noise. Next, we will also discuss the effect of beta using synthetic data. Lastly, the voice therapy samples and synthetic data are both used to compare Moana and Bayesian Online Changepoint Detection, or BOCPD. We applied Moana to data originating from recordings of voice therapy exercises. These include vocal exercises such as humming, lip trills, phonation through straw phonation submerged underwater, sustained phonation on vowels, and ascending and descending pitch glides, which are commonly used in actor training, singing, and speech language therapy interventions for individuals with voice disorders. The exercises are recorded in various noisy environments, for instance, in a home with a television or other noise sources in the background, at a sampling rate of 44.1 kilohertz. To assist in analysis of the exercises, it is important to identify the beginning and end of each vocal exercise. These exercises are not properly speech and differ enough that they defeat many different detection algorithms. The goal is to find change points to indicate where vocal exercises stop. We use the short-term signal-to-noise ratio, SNR, as a feature for distinguishing vocal exercises from noise. We assume that the first 20 samples are noise and use them to establish the baseline noise power. Here, we see the result of running both versions of Moana on an example signal, where it is able to successfully accomplish this task.
Next, we conducted an experiment to empirically demonstrate the effect of the beta parameter. We use Moana on a synthetic signal augmented with white Gaussian noise with a target SNR of 10 dB and varied the value of beta. As we can see from the table, beta creates a trade-off between the missed detections and the false alarms.
Last, we will compare our performance with that of BOCPD. BOCPD, used for this comparison, is based on an implementation found online. Both techniques were performed with the previously described SNR as the change point feature. For BOCPD, we use a Poisson rate lambda that maximizes the F1 score for each signal. For Moana, we use the same regression model as for the speech therapy exercises to estimate delta. Both algorithms were tested on the same 100 voice therapy exercises. A summary of the performance on all 100 signals is shown in the table on the slide. The table also contains individual results for 2 arbitrary vocal exercises, in addition to comparing performance on 2 synthetic signals augmented with noise, with a target SNR of 10 dB. Moana outperforms BOCPD in 101 out of 102 conducted experiments. The table shows that not only does BOCPD yield poorer results segmenting the voice therapy signals, but it also performs worse with synthetic noise signals. Both methods boast high recalls, but BOCPD achieves a significantly lower precision on all but one of the tested signals. We believe that Moana outperforms BOCPD because of its robust parameter estimation methods and compatibility with generic change point detection. It is also worth noting that even though the regressor is only trained on vocal exercise data, it still manages to find a well-performing delta for synthetic noise. This figure provides a visual comparison of the change points detected by BOCPD and Moana. We see BOCPD's lower precision is manifested as a large number of false detections. It is clear from the figure that Moana outperforms BOCPD on synthetic noise data and real vocal exercises. In summary, we introduce additions to the well-studied CUSUM that eliminates sensitivity parameters and adaptively detects change points in real time in any univariate signal feature in a scalable manner. In addition to dynamically estimating the CUSUM threshold H and the change sensitivity parameter delta, the resulting algorithm outperforms Bayesian online changepoint detection in various tests. An additional single tunable parameter variation was introduced that could be used in isolated segmentation tasks. The proposed CUSUM variations perform well even when Gaussian assumptions are not met.